This video discusses Newton's method for approximating zeros. And one of the funny things about this is that this is a very applied version of the calculus. Much of what we've done up to this point has been kind of abstract and not immediately useful. And so this is one of those things about the calculus where we really start getting to see some true usefulness to or application to real world problems. And now Newton's method for approximating zeros, this works for all kinds of functions. Now assuming a couple things. One, that the function is continuous on a chosen closed interval, and this chosen closed interval must include the zero. Two, the function must be differentiable on the open interval. And three, if the y values of the endpoints have different signs, then there must be a zero y value in between them, and that's the intermediate value theorem that says that. Now, how to use Newton's method? Well, we're looking for the zeros of a function, and so we're looking for those values of x where y is 0. The other thing we want to do, or that we can do then, is we can express the tangent line as in the form or in the point slope form of an equation. And in algebra, you would have learned the point slope form to take on a similar structure of this. Y minus y1 is equal to the slope, or m, times x minus x1. Now, in calculus, we're in functional notation for one, and the second thing we have is the power of the derivative, or at least we do at this point. And so if we just kind of put these things in, we have y minus f of x1. If we take and we guess as to what the value of the 0 is, as to be x1, then we can do that. Also, we take the derivative to find the slope, and that's going to be x minus x1. Now, when y equals 0, when we put that in, then we have 0 is equal to f prime of x1 times x minus x1 plus f of x1. So that if we solve for x, then what we get is x is equal to, and this is going to be x1, and then we're going to have a subtract off our f of x, or f of x1 over f prime of x1. Okay, so if you go ahead and solve for x from this, this is what you'll get, x1. Okay, so now that we have this, we have a new. So we're going to say, okay, now that we have that, this lets us be a new. Oh man, my brain is just fried for some reason. This is going to be a new estimate, and it should be closer because we're getting closer and closer to the actual 0. And so if we continue this, then we substitute x2 in, and we'll get x3 is equal to x2 minus f of x2 over f prime of x2. And now we have a new, what's called an iteration. Okay, each one of these steps is called an iteration, and we can do this as many times as we want. So that's how Newton's method is used. Now, in a more practical setting, and I put this little note at the bottom, for this process, computer programs capable of recursively defined functions are very useful, meaning that they use a previous input in the input of the next step. Excel and those that are like it that can run these calculations according to cell inputs can perform these very, very well and very, very fast. And so if you make a table and run that table in one of these programs, you find out very quickly that you can run it right down, and then you can extend it to however many zeros you would like. And the power of computers makes that quite nice. When they were first implementing Newton's method, of course, they didn't have calculators. They had abacus and some mechanical calculators, but not very many. But you had to hand calculate all of these. Well, you don't want too many iterations, so they came up with better methods pretty quick. Although Newton's method does converge quite quickly. Okay, so if you want to know how or why Newton's method works, because there are some restrictions on it, you can look for a proof in the book called An Introduction to Analysis, 3rd edition, by William R. Wade of University of Tennessee. And this is a book that I used for my advanced calculus course. One that I hope I pulled away more than my grade looked. It was a very difficult course for me, and it took a lot of thought power that I didn't have at the time. And so as I get better and better, I can go back and I can kind of read these proofs and logically follow them through. Okay, let's go ahead and take a look at Newton's method. In the general sense, if we want to go to the next successive approximation, then we put in the previous value of x, and we subtract off the previous y value and divide that by the derivative value of the previous x value. This is very, very, very difficult to say, but this is it. Okay, use all the previous data, the step previous to the one that you want, and that's how you'll figure it. And so certainly one nice way to do this is to just create some kind of a table. And this is where Excel and programs like it come in very, very handy. You can make a table of n, and then you also must find x of n, or x sub n for the subscript. You also need to find f of x sub n, so the y value. You need to take the derivative. And then from there, you can go ahead and recursively define this whole mess. And so I would actually, some books that I've seen will have another column in here where it says, well, take and divide the functional column by the derivative column, and we're going to skip that and go straight to the end. In this day of computers, this works out pretty quick. When computers, by the way, when computers don't know, this is a very good method for them to use. Now, does this work? I don't know. I don't know if that's what they use or not. And so you could simply fill out these columns for whatever function you're considering. Okay? And that's the easiest way to approach these. Now, we have a serious, serious issue here. And it's not immediately apparent that we do have one. But it is possible for this thing right here to blow up. It does that when f prime of x of n is equal to 0. Okay, so now if you think about this and you're trying to approximate the 0 of, say, for example, x squared minus the root of 2. And you're saying, okay, I want to use Newton's method to find this. Well, or I don't want that. No, that's not what I want. I want to have x, say, x minus 1 quantity squared. And I want to use this, even though I know I can find out, and it's not very bad, even though I can find out the root, I might be looking at something very, very similar, where it goes down, strikes the x-axis at one point, and then comes back up, or vice versa. Now, we run into a problem if that's a relative min or a max, because relative mins and maxes only occur at critical points. Critical points are defined by whether or if the derivative is 0 or does not exist. And so in the case where the derivative is 0, Newton's method fails because you can't divide by 0. Now, if the top, so if the function is 0 and the derivative is 0 at that point, x sub n, now there are methods that you can use to possibly get it to converge, but those will be covered much, much later. Okay, so now I just used a word to converge, and we really haven't talked about what that means. So convergence. In a nutshell, if the limit as x tends to some value c, typically to infinity, but the limit as x tends to some c of some function of x is equal to a limit, then the function is said to converge to the limit as x approaches c. And so many things for convergence, traditionally, things must converge down to zero. In other words, they're looking at the difference between, for example, and I think I addressed this in one of my previous videos, that the limit really is for all, whoops, back. For all x in the interval, there exists a delta greater than zero and an epsilon greater than zero, such that x minus c less than delta is equal, or implies that the difference between f of x and L is less than epsilon. Okay, then we went through that, and that was kind of the formal definition of the limit. But now the convergence is, okay, if it converges to that, then as x approaches some c, then we approach some number. It converges to that number. And that's really I don't really want to get into convergence as a very rigorous definition, but that is essentially the idea behind this convergence. Now, the opposite of that is to diverge, meaning it just blows up. If it converges, it eventually settles down to something. We don't know what that something necessarily is, but it settles down. If it diverges, it does not settle. These are normally used in series and sequences. However, you can always show that, well, the limit is nothing more than a sequence. And you just keep getting smaller and smaller and smaller, and you just show that the limit, or the sequence must converge as n goes to infinity. And that's effectively what they do. And so one way to test this, and it kind of moves along this idea, what's called the radius of convergence. And in this radius of convergence, you have a limit placed on Newton's method where if the absolute value of the function at x times the second derivative at x over the first derivative squared, this is basically the quotient rule. This would be the next iteration. If that is less than 1, then Newton's method will work. So Newton's method works. Now, it's not necessarily true that you can't have other methods work. This is only sufficient to say that Newton's method works. It is not necessary that this occur. And so that's another argument for another day. But if you go back and you look in this book, it's really good about giving some explanation into each step and how you can see that it does converge or it must converge.